Hello and welcome to this Chemistry World webinar, CO₂ storage, magic doors and machine learning. I'm Natalie Starkey from Chemistry World and I'm here with you for the next hour where we'll be hearing about how machine learning based atomic scale simulations performed with Matlantis can help rationalise experimental results, focusing on CO₂ storage. The webinar will begin with an introduction to Matlantis by Dr Rudy Coquet from Preferred Computational Chemistry, the startup behind Matlantis. We'll then hear from Professor Masaki Kawano from Tokyo Tech, who will explain how a copper-based coordination network selectively absorbed CO₂ at room temperature and retained it for over a week while exposed to the atmosphere. We'd like to thank the sponsor for this webinar, Preferred Computational Chemistry, whose mission is to contribute to a sustainable future by enabling companies to create innovative materials. While computational chemistry has recently made substantial achievements, some bottlenecks persist. The long computing time, problem-specific methodologies, and high-performance computing environment. Matlantis solves these problems with the fast, versatile calculation engine and browser-based user interface with no need for a special environment. So let's hear a little more about our main speaker today. Masaki Kawano has been a professor in the Department of Chemistry in the School of Science and Engineering at the Tokyo Institute of Technology since September 2015. He received his PhD in coordination chemistry from Waseda University in 1993. His research interests include coordination chemistry, supramolecular chemistry, in situ chemical crystallography, crystalline state photochemistry, and ab initio powder X-ray crystallography. Rudy Coquet, who will be giving a short introduction today, is a senior manager at Preferred Computational Chemistry. He received his PhD in chemistry from Cardiff University in the UK in 2005 and his MBA from HEC Paris in 2013. Now, as usual with all Chemistry World webinars, we welcome your questions for our speakers, which I'll be able to put to them in the second half of the webinar during the live Q&A. You can send in your questions on the GoToWebinar platform at any time during the hour. As a quick explainer, on GoToWebinar, there's usually a panel down one side of the screen, although this might be different depending on which platform you're using, especially if you've joined us via a tablet or phone. Now, somewhere on that panel, there's a questions box, so feel free to pop your questions in there at any time. We also have a few of our own staff on hand to assist with the questions and some colleagues from PFCC who will be working in the background today. But without further ado, let's begin the presentations. And please, as a reminder, do send in your questions into that questions box so we can get straight onto them after we've heard the presentations. So I'll welcome Rudy on screen first of all. Okay, thank you, Natalie, and thank you to the audience for joining this webinar today. I hope this will be very interesting and interactive. So let's start right away. So. My name is Rudy. I'm working for PFCC. PFCC, probably most of you don't know the name of this company. It's a new company. You see here on my first slide, actually, a brief introduction to our company. We actually just started 2 years ago as a collaboration between two other Japanese companies. So one is Preferred Networks, the and the other one is ENEOS. So this is the largest Japanese oil company. And what we are doing, actually, we are developing a new software, a new methodology, and we call this Matlantis. Matlantis is a high-speed universal atomistic simulator. And today, this is used already by 60 organizations and a bit more than 400 users. So you see, it's a young company, but we are making some very good progress. And you see here a lot of Japanese names, but we also have the first few foreign customers joining us. Now, what is Matlantis? So Matlantis is actually, I like to call it a paradigm shift. So today, if you run calculations for using traditional methodologies such as DFT, you will be facing a huge number of minutes and hours to complete your calculations. If you use Matlantis, because we are using our own neural network potential, so we are not using TFT, computation time will drop, and you will see in the next slides, this time will drop to just a few seconds. So what Matlantis can do
is actually compute and represent quite well systems that are from the atomic scale to the nanoscale. So classically, what you would be doing with DFT, of course, but also with molecular dynamics. So going from a few hundred atoms to 10,000 atoms is a very big step that allows you to study a lot of new systems, including even biological systems. Three key features of Matlantis. The first one is versatility, because we support a very broad range of elements. So today, we are covering 72 elements from the periodic table. So when you run your calculations, you just have to build your model with all the atomic coordinates. There's nothing else you need to do. Matlantis will then pick up the coordinates, the element number, and then run the calculations, the same way you would do with the DFT. The speed, of course, the speed, as I just mentioned on the previous slide, is about 10,000 faster than what you would obtain with DFT. So you see here on the screen a very simple example using a platinum FCC cell, where you have 3,000 atoms. It's not something you want to do with DFT, but with Matlantis, that would take about a fraction of a second to complete a single point energy calculation. And finally, but very important, the user friendliness. So as I mentioned, you just need to actually have your structure ready, open the browser, run the simulation, and unlike conventional machine learning simulations that you have used probably or have looked at today, Matlantis requires no data collection or training by the users. So there is no retraining, or you don't have to worry that Matlantis has not been developed for your specific system. You just run the calculation the same way you would do if you run DFT. Now, the capabilities, so accuracy, we compute energies and forces at the same level of accuracy as DFT. You will see that in the two use cases I have selected to present today. Security and scalability, we are actually proposing Matlantis as a cloud service. So this is running in the cloud via the Amazon Cloud Service. So the very, let's say, high security provided by global standard cloud system. And it's flexible, as I just mentioned before, because you run that in a programmable environment using Jupyter Lab. So if you can do some Python scripting, this is very powerful to run your calculations and to automatize things that you'll be running. The user interface is quite simple. You can interface it with both AAC and LAMPS. So the two can run. And you see here a very short example of how it looks. Physical properties are the traditional ones you will calculate with your DFT codes, for example, or MD codes. The mechanism behind Matlantis is like this. So Matlantis is based on a very large-scale atomic structure data set. So more than 22 million data sets, equaling to more than 1,000 GPU years that has been spent on our own supercomputing cluster and the PFN cluster. And this is connected to our own neural network potential architecture. This provides you what you achieve when you use Matlantis, which means that you can predict very accurately energies and atomic positions. What is so special about our neural network potential, so we are calling this PFP as preferred potential, is that our data set is generated by MD simulations using the machine learning model itself. So this is a like what you would do when you have a self-learning or self-play data set. And by doing this, we minimize the influence of the knowledge that would be entered if that this was done by a user, by a human. The second very important thing is that we include in our data sets disordered and metastable structures. This is a unique feature from Matlantis that allows you to predict transition states and as also represent unknown systems. So even though Matlantis was not trained with new or unknown systems, it will represent those systems correctly. This is the first use case I wanted to show you. So this is a very simple synthetic fuel catalyst example. Here the goal is to produce something out of CO that would be more interesting, so as a higher value chemical such as C5+. What was done here, more than 9,000 configurations were screened to find a catalyst promoter to decrease the activation energy of this reaction, so the CO dissociation. And this was done with Matlantis in about 2 weeks. If you do this with DFT, we estimate it will take you a year or more. Now you can also plot, you see on the screen, the activation energy calculated by Matlantis and compare that with DFT, and you see the mean average error is actually very small. It's 0.1 eV. Now, what we found is that vanadium gave a decrease of 40% of this activation energy. This was as well checked experimentally. You see here that a very good correlation both with DFT and also with the experiments. The second use case is a different one, but this is related to lithium-ion diffusion in solid electrolytes. So the LGPS to be more precise. Here, what we have done, we have run molecular dynamic simulations. The goal was to actually reproduce the characteristic features of lithium diffusion. And we have done that in 2 to 3 days in order to plot the Arrhenius plot that you have on the screen here at the bottom left. And you see we will produce what is well known, which means that the lithium ion will diffuse along the z-axis, which is the curve, or let's say the data that is in blue. And the x and y axis, you will see a much smaller root mean square displacement. We also calculated diffusion coefficients. So you see in red the Matlantis data, in black the DFT data. You see again a very good correlation. And we calculated the excitation energy, so 230 milli-electron volts against 210 for DFT and 242 for experimental. What I want to mention about those two use cases is that they are not part of the training data set. So Matlantis was not trained with these elements. So for Matlantis, those two use cases present completely new cases, which means that it's a proof you can actually screen and find new systems even though they are not part of our training data set. This is a customer testimonial that we like to show. This is coming from Toyota Motor Corporation. They are one of our users, of course, but they have tried running similar simulations for battery materials using DFT on their own supercomputer, using DFT on the national supercomputer, which is pretty fast, and they have used Matlantis. And you see in both cases, Matlantis is much faster than the DFT code. So what took them before about 3 months is now something they can do in a week. And they claim that with Matlantis, they can calculate roughly 10 million structures in a year. And we both believe this is a definite advantage to find promising candidates. Now, just to wrap up this short introduction before I give the word to the core of this webinar to Professor Kawano, I hope I managed to show you that Matlantis can accelerate mechanisms elucidation, can allow you to do large-scale screening to find new chemicals and materials, so discovery, and can facilitate the digitization of your R&D departments. We have a lot of news coming up, so please stay tuned. For example, we are opening next month our EU servers. We are going to also introduce our own MN core microchip deep learning processor powered Matlantis. So this is something we are working on. And we are also working on our own large language model that ultimately at some point as well will be combined with Matlantis. So these are news that I ask you to keep an eye on by following us. And with this, I would like to give the word to Professor Kawano, who will tell us more about how he's been using Matlantis to understand CO₂ storage. And that's very promising as well. Thank you.
Thank you very much, Rudy. That was a really useful introduction. I'd like to take the audience to a poll now, if that's all right. So we'll bring that up on screen now before we welcome our next speaker. And we can bring up the results so that Rudy and the audience can have a look. So people were able to select more than one answer, I believe, in this poll. So whatever applied to them, but it looked like first principles ab initio was the most popular answer there. So I don't know if that's a surprise to you, Rudy, or if those, if you want to say anything about those results.
So it's not a surprise. I think I mean, everyone in the computational chemistry or computational materials world has been using DFT a lot, and we see that as continuing for some time. But it's very interesting to see where this will go, and we very much like to hear from interesting potential users who would like to see how Matlantis compares to DFT. Yeah, very interesting. Thanks.
Brilliant. Okay, thank you. Okay, so let's welcome Professor Kawano onto the screen now.
Yeah, thank you. And thank you very much, Rudy, for your nice presentation about Matlantis. So today, I'd like to introduce our recent progress about the CO₂ storage material, so-called MOF. And also, I want to introduce the application of Matlantis. to explain the mechanism. Yeah, this work is collaboration with ENEOS Corporation. Okay, so yeah, first, let me introduce our research motivation. So our target material is a so-called MOF, metal organic frameworks. So some people call it porous coordination network or coordination polymer. Yeah. So actually, we started MOFs research about maybe 20 years ago. So that time, most of MOF chemists pay attention to the thermodynamic product. Yeah. So no one pay attention to the kinetic product actually. So many of people know the presence of some kinetic product. However, people didn't try to use this kinetic product. Yeah, because thermodynamic product case is you can easily crystallize. Then you can know the crystal structure by single crystal analysis. However, kinetic product case, most of case, yeah, you can obtain that only as a crystalline powder. So in this case, it's quite difficult to solve the crystal structure using a powder diffraction. Yeah, however, this kinetic product has a very interesting point. So first of all, of course, you can create a totally different structure from a thermodynamic material. And structure is different. That means physical property also must be different, right? So that's why we started investigating this kinetic product of MOF. Yeah, this is a starting point of our research. So yeah, I forgot to explain what is a MOF. Actually, you can synthesize MOF very easily using a metal ion and a breaching organic ligand by a self-assembly principle. Yeah, just mix together. So by itself, you can obtain the MOF structure. So next slide summarize our recent research interest. Yeah. So actually, we are interested in the metastable structure of a MOF. So then, how you can generate such a metastable structure? So we pay attention to the interactivity of a ligand. So if you use interactive ligand for MOF synthesis, actually you can easily trap metastable state. That means you can deepen a local minimum potential well. In this case, easily you can isolate only kinetic phase. Yeah, that's why we started designing interactive ligand. Yeah, it's not easy. However, we succeeded in them making a very interesting ligand. Then we combined kinetic and some dynamic control. Yeah. Then we created many kinds of MOFs until now. Then also we pay attention to the some space, not only space, but also potential in the void. That means if you introduce redox activity in the ligand, so you can create some redox active pore, redox active void. Then you can create very interesting material, porous material. So our research interest is exactly correlation between structure and function. So currently, we are working on these projects. So one is using molecular recognition ability of a MOF. We do a crystal sponge. Okay, crystal sponge research means if you can encapsulate your target gas molecule in a pore, you can determine the molecular structure by X-ray analysis. So even gas molecule is not crystalline, doesn't crystallize. Yeah, as long as if you can encapsulate the gas molecule, you can determine the molecular structure. This method is developed by Professor Fujita, Makoto Fujita at the University of Tokyo, yeah, in 2013. Yeah, so our MOF, it really works well as a crystal sponge. And another project is a reaction. So we are developing a MOF catalyst right now. Then using our redox active MOF, we make some device, fabricate some functional device. So in each case, keyword is a crystal structure. So based on the crystal structure, we developed a morph chemistry. So how you can generate the void? Yeah, this is also important point. Not only interactive ligand. So you need a strategy to make a void. So one of our strategy is to use tetrapod type ligand. Okay. So as you know, the tetrapod you can see along the seaside. So we use a tetrapod to protect the seaside, right? So the reason is actually tetrapod has many void. Actually, you cannot densely pack tetrapods themselves, right? Yeah, because of this shape. So this pore is quite important to cancel out wave power. So we pay attention to this ability to make some void, okay, in the accumulated structure. So first, we design this TD symmetry ligand, pyridine type ligand. So this ligand has 4 hands as a coordination site. Yeah, so if you use this TD type ligand, you can easily make a pore actually, or channel. So let me show some example. So using this TD type symmetry ligand and combined with this copper iodide cubane cluster. Okay, this is a Cu4I4 and 4-tetraphenol phosphine. So this is terminal ligand. So if you mix together in DIMSO at 186 degrees, so these materials can be dissolved. Yeah. Then when you cool down, yeah, rapid cooling case, you can get the kinetic product, kinetic network. So yield is quite high, almost at 100%. In the other hand, slow cooling case, you can generate a thermodynamic network. So surprisingly, you can selectively prepare this material. So this is supposed to be kinetic product. However, yeah, this one is stable enough. First of all, let me show the crystal structure. So kinetic product case, the future of the kinetic product is you can generate interactive site, this red circle. So this one is actually breaching iodide atom. So this iodide is facing to this pole. However, kinetic thermodynamic network case, this interactive site is covered by a ligand. So this iodide cannot face to the void. So using kinetic assembly, you can generate interactive site in a pore. So that's why we pay attention to this kinetic network. Then we tested the stability of the network. So even kinetic structure, this network is stable enough up to the 460 degrees. And we calculated this stabilization energy. So the energy difference between kinetic and thermodynamic network is just 1.5 kilojoule per mole. So yeah, even kinetic product, you can use this kind of a kinetic morph for application. So actually using this one, we adsorbed iodine using a chemist option. Using this interactive site, you can adsorb iodine in a chemist option manner. On the other hand, this thermodynamic network case, you can absorb iodine as a physics option. Yeah, actually using a capillary effect, yeah, you can strongly trap the iodine in this void channel. So let me start today's topic. Yeah, so title is CO₂ storage, magic doors, and machine learning. So actually, first I would like to introduce my collaborators. Actually, first, Mr. Shimada, he was my student. So he's a key player for this project. He has done most of the experiment. And also my staffs, Dr. Wada and Dr. Uso, and Professor Matsumoto. So Professor Matsumoto is coming from ENEOS. Yeah, he has both positions at the Tokyo Tech and ENEOS. Yeah, thanks to them, we achieved this achievement. Actually, surprisingly, the day before yesterday, this paper just online. Yeah, now in publish. Yeah, please, if you are interested, please take a look at this article. Yeah. So this slide shows some introduction of CO2 adsorption material so far reported. Yeah. So there are three types, actually, roughly speaking, yeah, there are three types of material. So one is a physisorption type. So using a relatively weak intermolecular interaction, so you can trap CO2. So in this case, using fluorine atom, yeah. So relatively, you can absorb this CO2 nicely, yeah. So another type is a chemisorption material. So this manner use acid-base reaction. So this pore, actually, there is some aiming group here. So using acid-base principle, you can trap CO2 in a chemisorption manner. Yeah. So in this case, you can strongly trap CO2 in a pore. And another type is a so-called gate opening framework. So gate opening framework case, actually, before and after gas encapsulation, actually this framework shows a very big distortion like this. So that means you can expect a big volume change, yeah, before and after gas encapsulation. Yeah. So, yeah, so far there are three types of more well known. So what about our strategy? So as I mentioned, we are so far using a tetrapod type ligand. So according to this result, we designed a new ligand, namely this one. So bimethyl skeleton, using a bimethyl skeleton, yeah, we made a pseudo tetrahedral ligand like this. So not exactly TD symmetry, but close enough. And the future of this ligand is actually this rotation is suppressed because of a steric hindrance between this methyl group. Yeah, so you cannot rotate this group. Yeah, relatively rigid group. And as a coordination side, we introduce a pyrimidine group here. Then what kind of a morph we can get? So we try. So according to this slide, we made two types of morphs. So this is a container, so-called a metal bomb. Yeah. So using this ligand, and in this case, copper iodide, oxidation state is 1. So according to this condition, first, we obtained a morph 1 here, and 74% yield, quite good. Yeah. Then if you heat at the 140 Celsius degree, measure product is morph 2. The chemical formula is Cu4I4L and acetonitrile. So in this case, yield is 58%, which is quite good. Actually, both cases, you obtain the mixture always. So unfortunately, we obtained the morph 1 and morph 2 mixture. However, my students smart enough. So actually this material has a different density. So using a different density difference, so we could separate very nicely like this. So this crystalline material is for morph 2. Yeah. So in general, it's quite difficult to separate the solid material, right? But using some proper density solvent, yeah, you can separate them, yeah, very nicely. Okay, let me explain the structure of morph 1 first. So morph 1 has a copper iodide dimer as a connector, like here, copper iodide. Then this copper dimer forms a 2D seat, yeah, 2D framework. Then 2D framework stack each other to make some 3D structure. Yeah, some crystal packing. Yeah, basically 2D structure, okay, 2D layer structure. Then if you look at this between layers, so you can see the isolated ball, which is quite small, actually. This is a dimension of 4 angstrom and 6.6 angstrom. So from now, I call this network 2D MOF, okay, or MOF1. Yeah. Okay, then what about the MOF2 structure? In this case, connector is a kappa iodide cubane. Last one was kappa 2I2, but in this case, kappa 4I4 connector. Okay, then another feature is that this is a 3D framework rather than 2D framework. Yeah, totally different from MOF1. Then this 3D framework is interpenetrating each other, doubly interpenetrating. Okay, then this MOF2 also has an isolated board. So dimension is like a 5 angstrom and like a 5 angstrom. Yeah. So now we know the structure. So we call this MOF a 3D MOF, okay? However, yeah, when my student reported this result in our meeting, we are so disappointed because no channel. Yeah, in this case, we thought, we cannot use this material for gas absorption, gas exchange. Yeah, because no channel. So we somehow, I was disappointed. However, my student never give up. So Shimada-kun tried to absorb gas anyway. So MOF1 case, 2D MOF case, actually, as we expected, no sorption occur for dinitrogen and CO₂ either. Yeah, so somehow reasonable result. However, surprisingly, MOF2 case, nitrogen case, no sorption at all. However, CO₂ case, somehow absorption occur. And also, as you can see, large hysteresis was observed here. Yeah, so we wonder what's going on here. Yeah. So, and this isotherm was measured at room temperature, okay? So this is also another important point. And the selectivity is quite nice over the CO₂ and dinitrogen. So we wonder, what is the mechanism of this material? Okay, first we check temperature dependence for sorption amount. So this is a raw data. Actually, we tested from 195 Kelvin to the 330 Kelvin. Yeah, we gradually increase the temperature. So this is a sorption amount summary. Yeah, unlike a conventional MOF material, at low temperature, no sorption occur. Yeah, at all. Yeah. Then if we increase temperature, so gradually, this sorption amount increase. Then decreasing again. So conventional MOF case, normally if you go to the lower temperature, you can increase the absorption amount, right? Yeah, but this material shows totally different behavior. So we are wondering, what is the mechanism of this material? Okay, first we check the crystal structure, so to investigate what's going on here. So, okay, so first, actually this network has acetonitrile as a guest. So in this case, unit cell volume is 4,418 cubic angstrom. Then if you put this crystal under vacuum at 246 degrees for over the 12 hours, you can remove this acetonitrile very nicely. Then we collected the data, this empty cage, at the 95 Kelvin. Then we observe structure very nicely. Then in this case, unit cell volume became smaller, a little bit smaller. So now 4,400 cubic angstrom. Then we introduce CO₂ at room temperature. So over the 1 day. So in this case, as we expected, we could see CO₂ molecule in a void like this. So each void contained one CO₂ molecule as we expected from a sorption measurement. So in this case, cell volume is slightly smaller, just 2 cubic angstrom is smaller than this one. So almost volume change is negligible. Yeah, so you can say almost no change occur, volume change occur. Yeah. Then, yeah, let me show the crystal structure in detail. So this is a crystal structure. Yeah, so CO₂ sit in the center of this isolated void, almost center. Yeah. So from this figure, actually this figure shows a distance between MOF and CO₂. So as you can see, notice this distance indicate this interactivity is only van der Waals contact. No strong chemical option, no strong interaction between them. Yeah, so this is typical of his absorption type adsorption. So then we investigate this behavior using FTIR. Yeah, using a vibration spectrum, we monitor this phenomenon. So first, before removal of acetonitrile, this is an IR spectrum. You can see here acetonitrile CN triple bond stretching band here. Then after removal acetonitrile, this band is disappear. Okay, so we should pay attention only this range now. Then after introducing CO₂, we can see clearly this carbon dioxide band here. Yeah. Then we monitor the time-dependent change of CO₂ band at room temperature in air. Okay. So this is right after 1 hour. Then this is 1 day later, 2 days later, and this is 4 days later, and 5 days later. So you can keep CO₂ at room temperature almost over the week. So this material surprisingly retains the CO₂ at room temperature for a long time. Then let me first summarize the nature of this material for CO₂ sorption. So this material has a high selectivity over the CO₂ and dinitrogen. And at low temperature, this material cannot absorb gas molecule. And surprisingly, no structural change. And even though no interactive site in the void, then this material owns a high retention ability. Then we decided to determine the investigate the mechanism, sorption mechanism, using Matlantis. So here, Matlantis is quite powerful tool to elucidate the mechanism. So actually, Rudy introduced very nicely about the Matlantis already, but let me rephrase again. Yeah, actually, we can calculate the atomic structure using Matlantis quite quickly. Yeah. So based on this initial coordinate, using a neural network model built by preferred networks, yeah, you can calculate molecular structure, some MOF structure very quickly. Not only MOF, of course. Yeah. Then you can determine the energy or force. Then you can understand physical property and the phenomena. And this slide actually shows very important data actually about Matlantis. So this graph shows a correlation between DFT calculation and Matlantis. So using a MOF database, okay, this is important. So this plot is coming from all MOF structure based on the MOF database, okay? So almost 90,000 structures, huge number of MOF structures. And as you can see, there are very nice linear slope here. So this means there's a very good correlation between the DFT calculation and the Matlantis. This means we can trust Matlantis result for MOF calculation, right? Yeah. Then we started the calculation. So first, we made some model using a CO₂. We put CO₂ in a void in a X-ray structure. Then we optimize the structure. Yeah. So in this case, surprisingly, calculation time is just less than 2 minutes. So if you calculate, yeah, this one using DFT, So using a workstation, I think over the 1 week, we spent more than 1 week. Yeah, of course, if you use a supercomputer, much faster. However, yeah, surprisingly, yeah, you can calculate this kind of structure. So this structure has even 320 atoms, and we applied a periodic boundary condition. Yeah, this is quite impressive result for us. Then we calculate the potential energy and the vibrational energy as well. In this case, it just takes 5 minutes, less than 5 minutes. Yeah, then we calculate the absorption energy. Okay, let me show you the result. First, comparison between X-ray structure and Matlantis simulation. So this is X-ray structure and this is Matlantis structure. So from a distance, you can tell how close each other. Okay, so first of all, the position of CO₂ exactly center of this void. Yeah, so Matlantis also expected that. Yeah, and from distance, yeah, very nicely, yeah, Matlantis realized this structure. Yeah, eventually we got a very good agreement between the X-ray and the CERN. Yeah. Then we calculate the absorption energy. So first of all, CO₂ case, 42.2 kilojoule per mole, and dinitrogen case, 26.4 kilojoule per mole. So from this result, actually we cannot explain the selectivity of this material for CO₂ and dinitrogen, right? Yeah, according to this absorption energy, somehow we should be able to expect some absorption of dinitrogen in this material. So, however, reality is we cannot explain that. Yeah. Then we calculated the diffusion pathway using a notch elastic band method, so-called NEB method. Yeah. So NEB method means yeah, you can calculate the minimum energy path from starting point to the another point. Okay. So NEB method calculate the minimum energy pathway like this. Yeah. So you can determine the diffusion pathway, yeah, based on this algorithm. Yeah. So you can know the transition state also. And the point is, Matlantis can optimize not only CO₂ position, but also frameworks itself. So if you use a DFT, and if you want to optimize framework as well, not only CO₂, in this case, a computer resource is quite huge. Yeah, but Matlantis case is easily you can calculate this kind of calculation. Yeah. So in this case, we spent just 1 hour for 320 atoms. Yeah, applied by a periodic structure. Okay, this slide shows the result for MOF1, okay, 2D layer MOF. So in this case, supposed to be no CO₂ absorption curve, okay? So this is a front view, this is side view. So please pay attention here, okay? This is actually connected is a copper iodide dimer unit. So as you can notice, this iodide is moving a lot, okay? So actually, initial position here, then this is a saddle point, a transition point, okay? Because of this large distortion, actually this activation is quite large, 100 kilojoule per mole. So this value is almost impossible, okay, for CO₂ to move to the another void. Yeah. So Matlantis predict, one case, no CO₂ absorption curve. Yeah, according to this activation energy. So what about the MOF2, 3D MOF? So in this case, you can see very smooth CO₂ movement from this point to the other. Okay, so in this case, activation energy is 55 kilojoule per mole, much lower than the MOF1 case, right? And also we calculate another pathway from this point to this point. So in this case, activation energy over the 80 kilojoule per mole. So you cannot expect some CO₂ movement from here to here. So the only diffusion path is from this one to this one. Yeah. And the next slide shows some structural difference between initial position, phase 1, and transition state, phase 4. Okay, as you can see, somehow you can see small difference, slightly shifted, but not like MOP1. Yeah, so just slight structural change allow the CO2 to move to the next point. Yeah. So most biggest change is this connector part. Okay. So copper cuban unit is this one. This bridging iodide is slightly shifted this way. So this void widen. Yeah. And this pyrimidine group also a little bit push out like this. Yeah. However, yeah, relatively small structural change occur. Yeah. Then next slide summarize some activation energy, some result. So for CO2 as well as dinitrogen. So dinitrogen case, activation energy is 66 kilojoule per mole. So which is 11 kilojoule per mole is larger than CO2 activation energy. So this is the initial position to the another void position. So this is a transition state, okay, position. So this probably this activation energy can explain why this material shows a very high selectivity for CO2 and dinitrogen. So the origin of this difference is probably coming from this kinetic diameter, because CO2 is 3.3 angstrom and dinitrogen case 3.64 angstrom, which is slightly larger than CO2. Yeah, because of this difference, yeah, actually this MOF has a very nice selectivity for them. Yeah. Okay, so this slide summarizes some sorption depending on the sorption type. So chemisorption case, you can strongly trap the CO2. So you can expect very large stabilization energy. And physorption case, yeah, you cannot expect so large stabilization energy. However, for regeneration, you need a small energy. So our MOF case, energy scheme like this. So first you need a little bit activation energy. However, you can stabilize CO2 with this amount. Then for regeneration, actually, you don't need this energy. Only what you need is this energy, because when you absorb CO2, heat will be generated. You can use that heat for regeneration. So eventually you can cancel out this energy. So our material case, you need only this energy, yeah, for regeneration. So that's why we summarize like this table. Okay, chemisorption case, selectivity is quite nice. However, for regeneration, you need a relatively big energy. So physorption case, yeah, in general, poor selectivity, but easy regeneration. But our material case satisfies both conditions. So that's why we named this is magic door system. So let me summarize my talk. Yeah, using Matlantis, we could explain the sorption mechanism. Yeah, even the MOF material and a huge number of parameters, you can quickly calculate this kind of parameter using Matlantis. And yeah, now actually for the future, actually using Matlantis, we designed a new MOF, and even we predicted some physical properties, sorption ability. Then, if we find a good material, we start synthesize such a material. Right now, we first synthesize, but we can nicely collaborate with Matlantis from now on. Yeah. Then finally, I'd like to thank my group members. Yeah, really, I appreciate their hard working. Okay, thank you for your attention. Yeah, that's all from me.
Thank you so much. We're going to invite Rudy back on screen now, as we've got a little bit of time left for some Q&A from the audience. So thank you to everyone sending in questions from the audience. We still have some time, so please keep sending those in. Some people have had their questions answered if it's something specific to them. There's been a great question from Jessica about if there's tutorials available on the website, and it seems that there is. So we can probably get that link shared in the chat for everybody. But do check out the Matlantis link that we shared earlier, because it seems like there's a lot of tutorials and information on there that might be of use. Rudy, do you have anything to add to that, things that might be useful for people trying to find out a bit more?
Oh, no, I mean, just go onto our website. You can easily contact us. You also have my email address. We do have a free trial that we propose to our potential customers. We'd be very happy to take the discussion further and discuss specifically what kind of system you would like to model with Matlantis.
Brilliant, thank you. So we've got a question about, okay, so it says, with high speed and accuracy, do you think Matlantis will replace density functional theory methods? DFT methods, and that's for Rudy. Right.
No, we don't think this is going to replace DFT. One simple reason is that we are not representing explicitly electron density in our calculations. And although this is very, it's let's say not needed in many cases, in some cases you still need to do that. You still need to represent, for example, a band structure. You want to calculate very precisely your atomic charges, which you can do with Matlantis as an estimation. So we do believe DFT will work hand in hand with Matlantis. But what Matlantis can do the heavy lifting work before the DFT part, screening thousands of configurations. Once you find the interesting one, then you can submit that to the codes that you run with DFT. So that's how we see it.
Brilliant, thank you very much. We've shared a couple more links in the chat there, so please do check out that. There's a couple of press releases that Masaki has shared with us, so please have a look at those at the end. Another question for Rudy. You've presented some impressive results obtained with the Matlantis. Could you tell us a little bit about its limitations, though, because I think that would be useful for people to understand.
Yes, we presented a lot of positive things indeed. Yeah, I mean, one obvious limitation that I actually just touched upon in the previous question is the fact that we do not calculate electron density. So you still need, in some cases, to use DFT or other things, just as coupled cluster, for example. But really, there are no true limitations today based on the feedback we have from customers. Maybe one limitation we see is in terms of system size that you can simulate. You can go up to, let's say, 8,000–10,000 atoms with Matlantis without too much issues. However, for some systems, like polymeric systems, or if you want to start studying biosystems like enzymes, where you have to go to even a higher number of atoms, let's say 50,000, 100,000. Today, this is still a challenge for Matlantis, but we are working on that. We are actually developing a, let's say, another, let's say, kind of Matlantis inside Matlantis to go even faster than what we are doing today. So I invite you to again to stay tuned to see what's coming next.
Brilliant, thank you. Let's go on to a question for Masaki. Can you tell us a little bit about the difference between the gate opening effect and the magic door mechanism?
Okay. Now audience can see my slide. Actually, gate opening case is actually required very large volume change. But in this case, if you think about the industrial application, volume change is not good for making a product actually. Yeah. However, yeah, our material case is almost no change of volume. So that means easily you can fabricate such a adsorbed, yeah, very nicely. So gate opening case really required a huge network change. Yeah, so in a sense, very flexible. So our material case is not so flexible, but still we can solve a gas molecule. So in general, gate opening case is if you remove the gas molecule, this framework will be distorted very largely like this. Yeah, so that means as above, also volume change occur. Yeah.
We've got a question from Suratu. Let me just get this one up on my screen. The question is about carbon dioxide and denitrogen gases. Can Matlantis be used to absorb other gases? In other words, what are the other applications for Matlantis? Probably that's for Rudy, I would have thought.
Can try to answer. Yes, of course, you can adsorb other molecules. We are not, as I explained at the beginning, we're not limited in terms of what elements, what molecules you can model. So as long as the elements you want to model are part of the 72 elements we cover in the periodic table, you should be able to study any systems you like. Of course, I invite you, if you try Matlantis, to compare with DFT or any other methodologies that you are using today, to see for yourself. I understand that I mean, machine learning and is very popular. Many people are making claims that this can work as well as DFT. But I really invite you to contact us to actually try Matlantis and see for yourself. And it's not perfect. It's not better than DFT, but you will see that it's doing a very good job when you compare that to other methodologies. So yes, the answer is yes, and I invite you to contact me, and I'll be happy to explain more and to let you try Matlantis.
That's brilliant. Thank you so much. I will get your email address shared in the chat again so that people have been reminded of that so they can contact you directly. But I'm afraid we have run out of time for today. We are bang on the hour and we've covered a lot of content there, and that's been really amazing. So thank you to both of you, Rudy Coquet and Masaki Kawano, for joining us today. And then thank you also to our audience for getting involved in the polls and asking some fantastic questions to our panel. Do keep in touch with them. If you want to learn any more, please do get in contact with them. Again, as I said, if you missed anything, you can go back when you get the recording in a few days, and you can go back and watch and check anything that you missed or didn't understand and need to go back over. So finally, a big thank you to Preferred Computational Chemistry for choosing to work with Chemistry World with this very insightful webinar. If you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for future events. And while you're there, then feel free to register for a Chemistry World account where you can sign up to our very popular reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. But that's all we have time for today. Thank you so much for joining us. I'm Natalie Starkey from Chemistry World, and I look forward to seeing you again in a future Chemistry World webinar. Thank you.
Thank you.
Thank you.